Okay, so in Pearson 3.3, in the Pearson 12 textbook, you've got questions 7, 8, and 9 at the end, and it's about a cantilever situation. So in a cantilever, what you end up having is essentially a bit of overhang. So if we draw all the different points at which a force would be acting, you're going to have a force here acting due to X, and you're going to have a force acting here due to Y, and you're going to have a downward force that you know about, which is going to be here due to the center of mass, right? And that's going to be equal to 9.8 times 900, and that's 8820. So just to sort of flesh it out a little bit, you know the distance here is 1.8 meters, and you know the distance between the center of mass and Y is 0.2, but you probably won't need to use that in this. Okay, so if you know the center of mass and the question's asking for the force due to Y, then the sensible thing to do would be to take the pivot, take X as the pivot. That way you don't have to worry about that, and you can find the unknown about Y. So at X, you can say that the sum of all the anticlockwise moments must equal the sum of all the clockwise moments. Because they're all perpendicular, you don't have to worry about any sine thetas. So I'm just equating the torque from the anti-clockwise. It'll have to be Y that's acting, because you know the center of mass is acting down, which is acting clockwise. So you know that this is going to be acting in a clockwise direction, and you know therefore that this must be acting in an anti-clockwise direction, opposing that moment. So with that in mind, you can say that the R value is 1.8 meters, and you need to know F. And in this case, R is 2.0, and you know, oh, it's 900 times 9.8, which we already know. Oops. And that means Fy is going to be equal to 2 times 900 times 9.8 over the 1.8, and what you should get is 9800 newtons. And that's fantastic. So that's the first one. Now, for question 8, it sort of says determine the direction in which Fx acts on the awning. Now, it's really easy for us to suggest that X will be applying an upward force, but if you think about it, it's actually not going to. So if you look at the diagram at the top here, you've got this big rigid post with its center of mass hanging over the edge, and you know that if you were to have your ruler, for example, and you were to push it over the edge of your desk, once that center of mass is over the edge of the desk, the ruler will fall down. Right, so what you would need to have to stop that would be a force, either your hand or something else, acting to push the ruler down at closer to sort of the X direction. But for this scenario, what that means is X must be providing a downward force on that block. But we can show this mathematically by saying, okay, well, all the upward forces, right? We've just figured that out. So far, all the upward forces are 9800, and all the downward forces, at the moment, it's just the center of mass, and that's 8820. So what we've got is, for this to be in equilibrium, all the upward forces have to equal all the downward forces, which means that the force from X needs to be downwards so that it makes up the rest of this amount. In fact, that's what the question 9 is asking. So it's asking for the force applied by column X. So that would mean that the force applied by column X is just going to be 9800 subtract 8820, and what you should get is 980 newtons down. Now obviously the only way for this to happen is if there was some sort of attachment point here at X where it could be pulling it down. The problem is that the diagram sort of insinuates that this whole thing's just sitting on top of it, and there's no attachment points apart from, you know, gravity pushing on it. But that's not the case at all. Looking at the diagram, you can see that this cantilever bridge, or this rigid object, will fall unless it actually has an attachment point at X. But yeah, there you go.